sort of the mission perspective, but from the student education perspective. So the goal here is to provide pre-college students, so high school, middle school students, an opportunity to be able to get into all aerospace engineering. So a CubeSat, some of you may be familiar with that name, you may have heard of that before. The first generation of that was a CubeSat form factor. So we had a 1U CubeSat with all commercial off-the-shelf parts in it that has basic functions of a satellite. When everything's said and done, all the parts put together, something like $100, $150. We're not selling anything, it's just plans for how to put stuff together and then turn it into a CubeSat that you can do lots of education modules with, and you can launch it on the high altitude balloons or whatever you feel like doing. So the second version is, we figure we'll shrink that down to the PocketQube level. You can bring down the cost even more and make it even more accessible for high school, middle school students, and any of those satellite programs to be able to get into the whole satellite education system. So what it is a CubeSat PQ, now the PocketQube version, and it's a satellite emulator. So the goal is to try to mimic as much of the functionalities of the typical satellite. So remote sensing, all of that stuff, and on the next slide I'll show you some of the hardware that actually go into it, and be able to provide the plans, how to put it together, share the ground station software, all of that, so that as many of the would-be satellite programs and at the middle school, high school levels to get involved, to be able to get involved in it. So it's got sort of the main things that you're used to seeing in typical satellites. So GPS for the position, speed, altitude, all of that. Inertial measurement unit for accelerometers, gyroscope, magnetic field strength type stuff, so that you could do some of the attitude, being able to measure some of the attitude and positioning and things of that nature. And a bunch of ADC, so that you could put extra customized stuff on it. So you could put extra solar panels, extra sensors, and if you want to put some more cameras on it, you can do that too. The current version comes with a thermal camera. It's 8x8, so it looks kind of Minecraft-ish, and but it's sort of a cool experiment that you could point at different things and see the hotspot red dot move around. That kind of experiments. The main processor is RP2040, and it'll be connected to the thermal camera as well as the environmental sensor to do some environmental monitoring type missions as you're flying it on the high altitude balloons or drones or whatever you feel like doing there. It's also got a transceiver, so we like to use LoRa. Pretty good range and then pretty easy to access. So two-way LoRa radio, and it comes with a ground station with the full ground station GUI software, so they could do two-way communication. And then what's really cool about that is you get to teach the students. So the concept of the telemetry, how to work with remote sensing, how to look at the real telemetry, analyze the telemetry, all of that. Cool educational things you could do with that. So all this is saying is what we're trying to do is provide, we're calling it authentic experience in aerospace engineering. So be able to provide students with experience in mission planning, soldering, 3D printing, system integrations, and then telemetry, analyzing, all of that, and in a small package that's affordable, scalable, and accessible for many of the students. If you like more information, you can come see me, as well as John Moore. Let me put up the first slide. John Moore, and then his high school, now college student team is basically the brainchild behind it. I'm just one of the users. I use this in my classroom to teach students some of the basic concepts in satellites before they jump into the full CubeSat. So I thought it was a great tool. I just want to kind of introduce that. And if you have any more questions, come see me after. Thank you.
Well, as I was mentioning, AITech's been around for 30 years. We build space electronics and systems. And today we're building what we call IQSat, which is a 6P satellite. Our heritage, it covers pretty much all the space industry. Any major company that you might think about in the space industry is one of our customers probably. And so I want to dive right into the 𝗖𝗀_SAT. The 𝗖𝗀_SAT is a 6P form factor, which you see the dimensions there. But we're not just doing the satellite, we're also doing the control room, the ground station, and all the communications in between. And that's actually where the biggest challenge is right now, because although we could leverage Orbital and the great work they've done, there's not somebody doing the same kind of work in the control room and the ground stations. The 𝗖𝗀_SAT, as a general, in terms of the general capabilities, it's about 1/3 the cost of a Starlink satellite. So that puts it into a very preferable cost factor for our customers. And we include a artificial intelligence and machine learning tool on it that does the image processing, allows us to detect patterns of life and patterns of behaviors so that we can detect anomalies and non-anomalous behavior. We have an uplink and downlink, as well as peer-to-peer mesh network. I'll talk about that in a second. It has a full ADCS, surprisingly. So in that 6P form factor, we have GPS, we have a star tracker, we have 3 reaction wheels, 3 magnetorquers, a magnetometer, gyros, and accels for all the access of the satellite orientation. And then we have an 18-watt electrical bus. In that bus, we can switch off any subsystem or power it on. We also have a radiation tolerant timer so that we can fly through the South Pole night normally without taking any stuffy hits. I mentioned a little bit about the features, and you can see those again here, but importantly, it's very modularized. Our concept is very modularized. We have an avionics bus, and to that, there's a common interface before and after the bus, and it provides a common electrical and mechanical interface for thrusters or payloads. So the satellite can be configured for a customer any way they want to very quickly. I mentioned I was going to talk about the mesh network and the constellation. I'd like to know what our plans are. Next year we want to launch 12 in a constellation format, and then after that we want to launch 1,000. So the 12 is basically a subset to determine and to get our technology ready in this level to level 7 for a bigger constellation. The constellation, if you can imagine it being the grid with columns and rows. The rows the horizontal rows would be the orbital planes, and the columns would be the intervals that we want to be able to travel in. This show here at 2,800 kilometers, that's roughly 5 minutes. Our field of view on our camera is 24 kilometers, so our orbits are going to be 24 kilometers apart. And it turns out that that's actually the most difficult part about this project, is how are we going to establish the constellation in the rows and the columns that we want. It's easy to put them in a string of pearls like you see here, but it's not easy to put them in a string of pearls with the next string of pearls being only 24 kilometers apart. That's beyond the capabilities of Starlink, or SpaceX. And so we have to have thrusters in order to maneuver our satellites into the orbit positions and maintain that position. I mentioned that we have to do also the ground stations and everything. This slide just talks about some of the communication needs that we need to have functional. Primarily, the data to our customer will come from the ground stations, or if they want more historical, relevant data, it will come from the control stations. And I guess I'm done. So there we go.
Good afternoon. My name is 𝗖cieः𝘁_𝗰𝘁. I'm from Puerto Rico. I'm principal engineer for Collins Aerospace Global Engineering Technical Center. Basically, my position is create a link between the companies, like in this case Collins, and the universities. And the idea is to show you today a little bit of the objective of the project. Basically, what is the problem we're working now? Collins basically have all the services for the aircraft around the world. And now when you are in the ocean, for example, you only have communication between the airports and the air traffic management using the geostationary satellite. Because you cannot have ability to communicate in 2 meters of reference box on data with the satellite. Now, we are proposing create a low Earth orbit, PocketQubes constellations. and trying to receive the ADS-B signals. The ADS-B signal is the signal that all the aircraft are launching every time when they are flying. This signal is in 190 megahertz, and we have an SDR radio receiving these signals and retransmitting this signal in UHF, basically. This is the first phase for the project, basically. It's an proof of concept. The idea is to expand this project to more big satellites. Then, how the PocketQube is a more economic solution. This is the option that we are using now for Collins, approving more money to continue doing research and continue including the academia in this type of project. It's a real project, and I have experience launching CubeSat in the past. When we put one satellite in Puerto Rico in 2021, basically with 3U. Now we are trying to launch a new version. And this is a collaboration between the Collins Aerospace, Inter-American University of Puerto Rico, Inter-American University of Puerto Rico, University of Puerto Rico, and Michigan University. It's a collaboration with different departments: mechanical engineering department, electrical, industrial, and computer engineering. What is the idea? Try to train the student, and we want to involve the student doing PDR, CDR, all the system engineering part. Yeah, this experience is good for Collins and for other aerospace companies in Puerto Rico that we are trying to grow. And the idea is producing 2P. And what is the status at the moment? We are working with the modeling. We have a class with the different universities in Puerto Rico, and our engineering teaching, for example, STK or a type of mission planning. They are creating PCB design. They are working with signal systems and with electronics. And finally, the idea is to integrate all the concepts, the radio, the antenna, the mechanical design, and trying to launch for the next year using, in this case, Alba Orbital. Now, this is the project that we are trying to create in Collins. If you have any question, let me know. Very short presentation. I'm very proud.
Okay, hello everyone. I'm Daniel Predeganda, I'm the CEO and co-founder of United Space. Last year we were up here to present development that we were working on, which was a first of its class, we believe, picosatellite thruster. And today we'd like to give you a bit of an update on that thruster, which by the way I have here in my hand, so if anyone's interested on very small propulsion systems, very cute propulsion systems, you can come afterwards and ask me. So picosatellite thruster, which is based on a common technology with other thrusters that we're developing called 𝗖cie. It's based on high temperature ionic liquids, and I'll tell more about that in a second. But basically, we as a company started developing a new kind of propulsion technology about 6 years ago. The idea was that we believe that in new space, propulsion should be designed in a way that you could give access to low power systems, high efficiency, high thrust to power ratios, very compact, scalable, and modular. These are all kind of like the signposts of new propulsion technologies for kind of like the new space environment. Particularly if you could also achieve, manageable and safe or green propellants, that would also be great. And low thermal loads. As you might know, a lot of electric propulsion systems out there have quite high thermal loads, which is obviously very difficult to manage already for large satellites and pretty much impossible to manage for small satellites like picosatellites. So we started developing, as I said before, a common technology called 𝗖cie, which stands for Adaptable Thruster Based on Electrospray and Powered by Nanotechnology. If some of you are not familiar with electrosprays, you can see a bit of a schematic of how it works here. But basically you have, let's say the main point of this is that you're using a propellant, which is an ionic liquid or molten salt. These are synthetic propellants that are made up of positive and negative ions. You can then use basically some geometric topologies and a clever use of electric fields to extract ions from that liquid and accelerate them to pretty high speeds, actually, of around 20 to 30 kilometers per second. So, as I said before, 𝗖cie is kind of like a common technology, and in fact, it's not only a technology for picosatellites. We are presently developing both nano and pico, which are two versions of our system. They're based on quite a lot of commonalities, both from the electronics to the propellant management system to the emitters themselves. And in the future, we will be developing also a larger system targeting something like 100 watts, which we believe is also important for a lot of the slightly larger systems, satellite systems that we're seeing coming out. So Athena Pico, which is again what I have here in my hand, is this thruster right here. You can see, let's say, the main components on the top right corner. So pretty simple system with, let's say, electronics, some, let's say, containers for the propellant, which is, by the way, is stored in solid format until it reaches orbit, at which point we melt that propellant and are able to fire it. And then basically our proprietary emitters, or electrospray emitters, which are kind of the big, I think, IP behind this whole project. So just to talk about maybe a couple of points in terms of the performances here. So specific impulse, 450 seconds. I know that's low for most EP systems, but when you consider the compactness of this system, it's actually not that bad. We are going to be trying to increase the specific impulse with future iterations. So we'll be hoping to reach something like 700 seconds, which brings us closer to being kind of like an acceptable electric propulsion system. The wet mass is around 100 grams, maybe a little bit more, so 120 grams. So that's, again, quite small for a propulsion system. Nominal power is 2.5 watts, but we can go up to 5 watts depending on the thermal environment. Again, remember that we have to melt that propellant in order to be able to operate it. And I think the two biggest points here are the thrust. It's 220 micronewtons of thrust, which actually is comparable to some systems out there that are 10 times the power that we have on this one. And this is mainly due to the selection of the propellant that we're using. And then the total impulse, which is 80 newton second of total impulse. Again, not that great for an electric propulsion system, but considering how small it is, it's actually, I think, quite interesting for some missions out there. The operational lifetime is about 100 hours. We've already demonstrated that, and actually beyond that on our ground tests. So suited for missions with let's say those kind of operational times expected for electric propulsion. So last year we presented this kind of point of proof of concept, that we have on the left, where we're kind of like assembling things on a laboratory environment. And this year we've now moved on to, again, more of a let's say complete system. You can see actually one half of these emitters on the middle image there, and to the right you see our vacuum chambers, where we use some custom diagnostics to be able to characterize the performance of the thruster. Maybe just to talk very briefly about what the thruster could do. So if we were looking at, for example, like a 6P satellite, I'll leave it there, and you can ask me later what you can do with the thruster. Thank you.
So this is Unicorn 2, if you haven't seen it. It's a 3P satellite. We've launched 17 of them now into orbit. We'll chuck it out of the bag, you can have a look at it later if you want. So Alba Orbital Unicorn 2 is our flagship platform that we're currently working on, launching. It's 3P. We've done like 70 plus pictures, I think we're 76 currently as of last week. We've launched 17 of them. It's got a big solar panel, it takes pictures of Earth. You may have seen online we posted some pictures of Unicorn in orbit. This is quite a nice one we got of Toronto. So the wider thing with Unicorn was more just to show that you could do useful stuff on a PocketQube. And when we started Alba like 13 years ago, it was very early days in this technology obviously now, and we're getting there. We're nearly launching the 100th PocketQubes community. So we wanted to show people that you could actually take nice pictures of Earth from a very small form factor. So these are a lot of US shots. This is Scranton, Pennsylvania, if there's any office fans in. This one's in Libya, so there's a lot of trial and error, to be honest, to get this system going, and there's a lot of photos that probably aren't worth sharing, and they're very like all white or all black, and that tends to be how, if you're making a camera payload in orbit, that's how things start. And it took us quite a lot of trial and error, and I think that's really like one of the great things about PocketQubes is we were able to iterate and fly and try. This one's in the Netherlands, you can see like the port of Rotterdam. So yeah, basically we've been iterating it, we've been playing around with the camera settings, we've been changing the exposure levels, the gain settings. And we actually did this in Scotland, so this is where we were from, so unfortunately Scotland's very cloudy. So we've not been able to get a good shot of Scotland yet, not through lack of trying. So at this point you start coming to the Earth observation and you finally get to orbit and have a satellite that works, and you get that. This is Florida, so there's some people from Florida in, so we got a nice one at your beach there, a nice one at the ocean. And these are still quarter scaling, so we're still quite constrained on the downlink. We're still trying to ramp up UHF and our S-bands systems. And ultimately, we should be able to bring down these pictures very regularly at much higher resolution. So the pictures you're seeing are probably around 120 meter GSD, so each pixel is about 120 meters, so you get quite nice photos of large areas. This is Colorado. We work with the national parks, and we're basically doing a lot of target practice on a bunch of national parks out west. So, and the great thing about being out west is the weather is very clear, so it's a great place to take pictures. This is New Mexico, and then basically we have another one here from Utah. So this is one we took. The next one is one we took, I think last week, and we put it out a few days ago. So this is the Utah one. This is just east of the Archies National Park. These are all shot on PocketQubes. They're all still pretty low res, so hopefully next year we'll have some nice high res ones for you guys to have a look at. This is Japan. This is very cloudy in Japan, it seems, when we were overhead. Like, why are we doing this? I mean, we're building this business around Earth observation as well as the rideshare stuff that Fraser was talking about in his talk. We're trying to demonstrate you can do useful stuff. We actually don't know where this is. ChatGPT doesn't know either. So if there's any geoguessers out there that are looking for a challenge, then I challenge you to find where this is on the planet. There's no GPS on the current generation, but the next generation will have the GPS on it. Well, thank you. Hopefully I didn't run out of time. But yeah, thanks very much.
Hey guys, so my name's Paul. I'm the CEO of Solid State Propulsion, and I don't want to get gonged, so we're going to dive right in. So, what is solid state propulsion? Effectively, we're not making solid rocket motors for SLS, which a couple of people thought we were, but we're making plasma propulsion, electric propulsion that is completely solid state. So that means no liquids, no gases, no big xenon tanks, anything like that. And there's a couple of reasons why that's quite groundbreaking, quite relevant, especially to small platforms like PocketQubes. So the first one is there is zero warm-up time on a system, so we can fire in like under a millisecond as soon as the capacitor bank is charged. Then a big one is if you have liquids, you can get sloshing, and then that can cause vibrations, and that can kind of affect Earth observation. So that's quite a good one to just have everything completely solid, super rigid. Then a big one is because we use solid metal fuels, we have much higher densities. So even without like including the tank mass and stuff, we're typically 10 to 20 times denser than liquid or gas propellants. Then another one, especially for PocketQubes, when you're integrating to launch vehicle, you have to pass the like range safety, and if you have anything pressurized or explosive, that can be a huge nightmare, especially for lower cost, very small missions like PocketQubes. So just eliminating that is also quite a nice feature. And then another one, you'll actually see the electrodes, because I brought our first product, the Pocket Rocket, so we'll see if we can do a live fire demo there. But because we use solid metal fuel, and that is actually the fuel in the electrodes, there's no issues with oxidation, and you can even fire it in atmosphere, which we will attempt to do. So yeah, that's pretty much it. And then maybe the last two things I'll just say is that, especially if you're planning PocketQubes or missions kind of in the next few years, this is the F10.7 solar line. So it's not a great time to be launching a satellite. There's a lot of drag. And so we've run some calculations. We can chat more about it, but effectively, with a representative, say like 306P PocketQube, you might be looking at as low as 7-month lifetime, which is not ideal. But if you have some propulsion, you can really combat the drag. Cool. So this is Pocket Rocket. As you can see, it's PocketQube form factor. It's about half a P. Yeah, and I'll be keen to show you guys later, but we can turn it on and we should get some arcs. Yeah, there we go. Cool. Awesome.
Everybody coming. It's great to see so many of you here. It's great to see enthusiasm for PocketQubes. I'm going to really briefly, so I don't get taken by the gong either, about the launches and what the kind of thing we do. So these are the 9 launches we've done so far. We did 2 of Electron and did the rest with SpaceX Falcon 9. And the main reason we go with SpaceX is pretty simple. They're really reliable and they fly all the time. When a customer comes to us and they're booking a launch, we don't want you crossing your fingers and hoping you're going to get up to orbit. You're getting to orbit. That's a big thing for us. You see this 9 up there? The slide will be changing very, very soon because we've just integrated our 10th launch. So that'll be 100 PocketQubes in our 10th launch. So again, it's great seeing the growing Pocket community, and we're so glad we can launch so many of you. So here's the next 100. We will launch more with you. Okay, so this is our pricing structure. We're very transparent about our prices. Again, we want customers to come and know what they're getting. So there's a price point you can go towards, and you can see actually this is really affordable, this is achievable, we can get to Orbit. So for a 1p, you see on the far left there, that's 25k euro, and a 2p is 40k euro, and a 3p is 60k euro. So how do we get you to Orbit, apart from strapping you to the rocket? We do it with our very own in-house developed Alba pod. This is by far the most reliable way to deploy your PocketQube to Orbit. We put 19 of these up. It's launched 53 PocketQubes in total out of the whole 96 that have ever been launched. Goes up to 6p, so we can do a variation. If you want to do 3p or 2p, or somebody wants to do a 6p, they're absolutely able to do that. We do have quite a few flights. We actually might have another one just coming up soon, which is not on the slide. I will update you guys if so. The next two have sold out, so that's Q4 2025 and Q1 2026. And the ones after that with very limited capacity is Q2 2026 and Q1 2027. So if you're wanting to launch the next year and a bit, I would definitely come and give me a shout. People are developing PocketQubes really quickly, so even if you're halfway down, somebody might jump in and book it tomorrow and take the slot. So please come and find me if you want to launch. So yeah, that is pretty much it, but please come and find us at the booth if you have any questions. I'd love to read more information if I can. Thanks.
So we're Bright Ascension. So we are, yes, we're based in Scotland, in Edinburgh. We're a space software company. We specialise in mission critical software. So we launched, or we were responsible for providing the software for the first launch in 2014. It was UCube 1. Since then, we've been responsible for more than 50 CubeSat and SmallSat launches of varying sizes, and certainly has been involved in a lot of different types of projects, so Earth observation comms, and a lot of in-orbit demonstrations. So we've got clients all around the world, and certainly we've been involved in a lot of collaborative research and development activities, working with all sorts of different industries, commercial as well as institutional. So we're very aware that PocketQubes have a very important role in the world today. It's cost effective, it's certainly lightweight and easy and deployable, and it's great for demonstrating in new technologies. So we recognise this, and we've had a number of customers come to us and said, right, we're on a journey. We've got technology that we want to grow, and certainly we're looking for further commercial success. So this is not everybody, but for those that are on that journey, then they're looking at what happens next. So that transition can be a challenge. So there's lots of hardware to consider, and often everyone thinks about hardware. They might go and book a launch and then realise, hold on, we need some software. We need some software on board this spacecraft to ensure that it runs properly. So how do we ensure that is the case? And certainly organisations we speak to, they may have a lack of resource or expertise at the time. They're still bringing people into the organisation, and that means that there is a steep learning curve to consider as well. And it can look expensive, and certainly lots of testing is required as well. Helix is our solution. It's a range of solutions, kits, so software development kits, as well as off-the-shelf applications to enable end-to-end solutions and capabilities. So we have lots of clients that come to us and will use one of our modules. They may well then take on a second or a third. But the whole idea is speed, so improved pace, ease of learning. So what we mean by that is we provide tuition, we provide support, we provide training on how to use our kits, and of course how to use our applications. So what it does mean is that our clients can get, through our modular approach, they can ensure that indeed they can build onboard flight software very, very quickly to get to launch and to ensure they've got a reliable mission. So the development can be rapid. We've seen clients come back to us saying, we've saved 6 months in our build. Some have actually said more. Some have come to us where they've been working with, because they've chosen OBC and the subsystems and the comm stacks, and the payload, all from the propulsion, all from different places and different providers. So there is no software that really just drops in. They've got to design it. So that uniqueness is easily resolved by using our flight kit. It does mean that lower cost goes through time. It does mean that you can reuse the software that is created using our kit. So there's components, there's libraries, there's all owned by you as you build it. It's easy to do, and it does mean that clients can save a lot of money and they can get there very, very quickly. We do also provide ground software. So those who are looking for ground software right now for PocketQubes, we can help as well. So the whole approach there is not only do we talk about being vendor agnostic, but also you can have a heterogeneous constellation. So really, just one last thing I wanted to talk about was there's a case study here for Troll, TRL in Czech Republic. They came to us, they had 6 months to build a satellite. We enabled them to get that mission out there, and it worked, and it was a success. And this was all about making sure that they did the time and got it correct. So for that, if you want to understand any more, if you want to speak to us, we're at stand 1014. We'd love to talk to you and share you more information about how we can help you in your journey. Thank you very much.
Hello, I'm Shamir Banerjee. So this is kind of last minute, so all I've got is my website. But what I'm developing is a new propulsion technology, which apparently is very popular with the community. I thought it was such a new and cool idea, and then I've come to realize everybody's making their own little water jets these days. So mine takes a little different take on it. I'm using inductive heating as opposed to, say, the old standard resistive heating, and not like the electric type stuff. As a result, you lose a lot of ability, so this thing is not going to the moon ever, but the idea behind using a really reliable old tech is that you can deorbit, you can do orbital maintenance, and do some collision avoidance. I'm at TRL3. I had a little boost from the NASA Tech Leap Prize Challenge this past spring. I didn't win the prize, but they said, hey, listen, you got a great idea, let's go forward, or you should go forward. So anyway, the thrust I've come up with is about 8 newtons, an ISP of 60 to 80, and so that results in a delta V for a PocketQube form factor of around 100 to 180 meters per second, which is enough currency to get you a little bit of what you need. Keep you in orbit for a little while, deorbit, and dodge a couple objects. So that's mostly what I've got. I don't have a fancy demo, sorry, that was awesome. And to talk a little bit, I guess, about the tech behind it. I don't want to share the magic secret, but everyone has had an inductive, or not everyone, but a lot of people know what that inductive stove is. So it's an old idea, and you got a coil in there, it heats up the water, and if you heat it up enough, you superheat it, and it gets you some power coming on the outside without having to do any deal with a lot of the technical challenges of the more high-tech electric stuff. And there we go.
Good afternoon, everybody. So I'm 𝗖cie from PocketQube. So we're a company founded in 2022. We're based in Belgium. And currently we're with 27 employees. So we have grown about 10 employees compared to last year. We mainly focus on ADCS systems, but mainly at the moment we sell star trackers. We have a whole range of star trackers, but I'm going to focus on the smallest one we produce because that's the most interesting. We have our Twinkle star tracker, so I have it here. This is real size. It's 35 grams. The device itself it has internal processing, so it's not only an optical head, it also does the processing of the stars internally. So it's basically you hook up the power, communication, and it outputs the solutions to the ADCS system, to the home computer, or whatever you want to do with it. For the small size, we lost some accuracy, so we're 3 arcseconds 1 sigma plus Bohr side right now. It's pretty good for the size, in my opinion. These values still have to be proven, so in February will be the first launch of the device, and we will send more to space in August. So hopefully it will then survive it, and that we can also get those numbers that we're committed to. At the moment it's a refresh rate of 10 Hz, so it's pretty good at some slew rates, and it's all autonomous. So you turn it on and it can do all the processing, everything itself. It's a small calibration you have to do in space to improve the accuracy, but that's mainly it. We also have a demonstration mission in August that uses 4 of these in half a U. We have 4 of them, and then we do we put the data together to have a higher accuracy and more availability. So it's still a trial. The device itself we can still already produce, and we also already sold some, but we're not now at the stage of sending it to space. One of the limitations the device currently has, there's no internal baffles. It's literally as small as possible. So we opted for external baffles that we can provide when requested on. I kept it pretty short today. That's it, honestly. We have not more to say about the device itself. If you want to buy, you can always drop by the booth. But yeah, that's it.
So yeah, just wanted to mention that we run a PocketQube conference. So this is a kind of taster event of what the conference is. So we run that every year in Glasgow, and some of the speakers that were speaking in Glasgow are speaking today, and then there's some new speakers here. So if you guys are interested in any of this, or you want to participate or actually meet a lot more people, that event typically has like over 100 people, around 30 talks. We have like 10 trade show booths, something like that. So if you're really into it, you want to learn more, then the Glasgow event will be happening March again, so 25th, 27th in Glasgow. We do early bird tickets are on sale soon. Yeah, we've not done that yet, we need to do that. We've been busy with trade show booths, so forgive us for that. They should be coming out pretty soon. It's 2 days talks, and then 1 day we do tours of the PocketQube factory in Hillington, Glasgow. So if you guys want to come and see how we produce lots of unicorns, we do some behind the scenes stuff, and we bring folks around and show our production and things like that. And it's really great for networking and really just sort of building your network, because a lot of people know us because we're like very loud and proud about PocketQubes, obviously, but there's so many other people's stories. We're trying to get those folks to tell their story basically, and it's not just us who are trying to push it forward. So I just want to say thank you for coming along. Hopefully you guys enjoyed it. Hopefully you learned something new and you've seen some new stuff that you hadn't seen before. There's quite a lot of hardware at the back if you guys want to check stuff out. We have the giveaway 1Ps. I'm sure there'll be live demos and everything in between, a lot of hardware. So yeah, thank you everyone for coming along, and hope you enjoyed it.